so let's get going. So we're in the middle of the slide deck called Lesson 2. I think somewhere around here was like the last slide we showed about how two different ways to try to compute the entropy by the third law method and second law methods. And this is sort of summarized. So from yesterday, we had a big discussion about fuels, about how convenient they are, and that's why we use so much of them. But if you list all the requirements you might have in an ideal fuel, and then you look in the world, there is no material satisfies all those requirements. So then you have to have a discussion about which of your requirements you're going to slip on, relax in order to actually have a solution. Or you're going to find some completely different way. And in particular, the current fuel system basically satisfies all the requirements pretty well, except for the CO2 emissions is the main weakness of the current system. We discussed what you want and need in a chemical kinetic model, all the different parameters you need, all the different information you need to know about what reacts with what, and also what a species in a dividing surface means. And therefore, from that definition, you can define the classical mechanics expression for the rate coefficient KFT. We talked about how helpful or essential it is to know the thermochemical parameters for all the species in your model. First of all, it gives you the true equilibrium. If you have all the species and you have all the parameters, then you can compute the true equilibrium concentrations. Also, you can compute the heating values. And also, you can compute all the reverse rate coefficients. That last point is really important from the kinetic modeler's point of view because it removes half of the unknown parameters from your model. So you know if you know the forward rates, you automatically know the reverse rates. And that's because they're related by the equilibrium constant, which is related to delta G, which you can compute. So then we said, well, we want to have these thermochemical parameters. And our subject today, to begin with, is how do we get them? How do we get these numbers? How do we get the enthalpy? How do we get the entropy? Many of the numbers we actually get from statistical mechanics. So I'm going to try to give a quick class in statistical mechanics here. I should warn you that most people would take this as a semester class. Maybe 2 semesters if you have a slow undergraduate program. And so this is kind of the quick version, an hour or less. There's this quantity called the partition function. That's the sum of the Boltzmann-weighted number of states, basically. It's how many different possible states your system has weighted by Boltzmann factors. And so you need to know the energy of each state. That's the EI. And according to the laws of quantum mechanics, only certain values of EI are possible. So states only have certain quantized values. If you were in a classical mechanics world, you'd have a similar expression, but be an integral because you'd have all possible energies be possible. But in quantum mechanics, it's just a finite sum. And if you know Q, it's amazing. That's actually enough to know everything about your system from a point of view of thermodynamic equilibrium. So for example, if you want to know the expectation value of the energy, the quantity that thermodynamicists call U, that's just the average value of E. So you have your Boltzmann weighting factor, your average value of E, and it turns out that is just the derivative of the logarithm of Q. Now, if you just do that derivative yourself out, you can show that turns out to be the expectation value of the E of the energy, which is what you mean by U. Similarly, for the Helmholtz free energy, if you do it out, it turns out it's very simple. It's just a negative KT times the logarithm of Q. And the entropy is more complicated, but there's the expression for the entropy. So if you knew what Q is, you know the entropy, you know the enthalpy, you know the U, you know the free energy, you know everything. All the quantities. The heat capacity is just another derivative of U. So you have them all. So if you just know how Q depends on T, that's enough information to know all this information. And in order to construct Q, the only parameters that really go in there are the energies. And if you have an energy that's repeated, it would give you a degeneracy. That's the G. So the key question is, how do we compute these E's? You need to know all these energies. And let's start with just a single molecule. How do we compute them? So first, if you're going to try to compute something about energy of a molecule, you need to know the potential energy. So we can, the kinetic energy of the atoms is simple, right? It's just the momenta squared divided by 2 times the mass of the atom. But the potential energy is quite complex because the atoms interact with each other in a really complicated way with quite strong interactions. And so we need to know this potential energy surface. V is a function of the position of all the atoms. And unfortunately, it's usually not possible to measure V of R. As far as I know, there's no experiment that measures it directly. And so you have to compute it, typically. Now, the forces between the atoms are basically electrostatics. So the origin of this is super simple. It's just electrostatics. The electrons attract the nuclei repel the nuclei, the electrons repel the electrons, and the balance of all those forces is what's holding the molecule together. However, the complexity here is the fact that the electrons are so light that they are quantum mechanical. And the quantum mechanical effect is huge. And you can't try to compute the electron motion classically. It doesn't match at all to experiments. You have to do it quantum mechanically. The quantum mechanical equations are actually pretty complicated. Now, I would say, actually, even if you're doing electrostatics, it'd be pretty complicated. This would be what's called a many-body problem. And it's possible to do it with modern computers, but it's certainly not trivial. But the quantum mechanics equations are worse. And so we'll talk about how we're going to try to do with them. But we know the equation. So the equation for quantum mechanics is called the Schrodinger equation. And it's an eigenvalue equation. And the lowest eigenvalue is the value of V of R, which we want. I'm going to write this thing all as V of R to remind you that when you change the positions of the atoms, the potential energy will change. But in all this next section, I'm not going to move R at all. So I'm just locking R at some geometry. And I just want to compute the potential energy that corresponds to that geometry. And then I could repeat this for many different geometries to construct what's called the potential energy surface of how the atoms are, the potential the atoms are feeling as they move around. But let's just even try to get it for one geometry is already a pretty big problem. Now, the Schrodinger equation is a partial differential equation in a very large number of coordinates. So many of you have done partial differential equations in probably 3 dimensions, like x, y, z, and maybe 4 dimensions, x, y, z, and t. But this one is a partial differential equation in 3 times the number of electrons coordinates. And for a lot of molecules, you might have something like about 100 electrons. So this is a PDE with 300 different differentials. So that's a lot of coordinates. And so that makes it really hard to solve. And in addition to being a pretty hard to solve PDE, there's extra constraints that to be physical, the solutions have to satisfy some certain symmetry properties. The most important of these is called the Pauli conditions, which means that if any time 2 electrons switch, if you take your solution and you switch any of the 2 coordinates of 2 electrons, you have to change the sign of the solution. That's a very peculiar extra condition that you have on your solutions that are allowable. And it makes this a very specialized kind of problem that you probably have not dealt with before unless you've dealt with this exact problem before. And so except for some really trivial cases, the Schrodinger equation is too hard to solve exactly. There's no analytical solution. And even you can't even brute force it numerically except for really small cases. So you're not even sure you know what the real solution is in general. So what people do to solve it is they expand the solution wave function in a finite basis set. That means that they write their solution, which is a thing called a wave function. It's like a wave equation is what the Schrodinger equation looks like. And you're trying to compute this sort of amplitude of the wave at each position, except it's at each position of all electrons. And they'll write that as a sum of some basis functions that are specially chosen to make it easy to solve. And then you'll try to adjust the coefficients. So the way it looks like this. So you have an equation that's a differential operator. H is a differential operator that operates on the wave function you're trying to solve for. And it's an eigen equation, so you're trying to actually get this V of R is what you're trying to compute, but all you know is H. You don't know this wave function. You don't know the eigenvalue either, and you're trying to compute what the lowest eigenvalue is of that equation. And H depends on the R's, which are the positions of the atoms. That's because the nuclei, where they are, will change where they attract the electrons to be. There's an electrostatic term. And also the repulsion between the nuclei. And it depends on the positions of all the electrons, and then also differentials with respect to the positions of all the electrons. And so this wave function is a function of the positions of all the electrons. This might be 100 coordinates. That's what that wave function is. So to try to simplify it, we're going to expand this function of 100 coordinates as a sum of some functions of 100 coordinates that we chose ourselves to be ones that are particularly easy for us to handle. And then, but we don't know the C's. So we're going to try to transform this problem into a problem of trying to determine the unknown C's and those coefficients. So that's the idea. The way that's done is you take this equation, you plug in this approximate solution here with the unknown C values. And so now you have an equation that looks the same. You multiply both sides by a test function, which I call key, on both sides, and then you integrate. And so on the left side, you get the integral of key times h. H is this operator acting on the wave function. This is going to be this expanded as a summation here. So this is this integral on the left, but I expanded c in here, so now I have a sum over all the coefficients times all these phi n's, my basis functions. So that's what I changed the left-hand side to look like. And these integrals, I know what key is and I know what phi is because I chose them both. I chose the test function, I chose the basis functions. So this is actually an integral I can integrate because I know what h is as well. Schrodinger told me what h is, what that operator is. So everything inside this integral I know. And so I could just integrate that either analytically or numerically depending on whether I know the analytical integral. And then I'll have some basically big matrix, indices indexed by m and n, multiplied by my vector of unknown coefficients, c. So I've turned this sort of left side into something that looks like a matrix equation, where I know the matrix and I just don't know the vector. And on the right-hand side, I have my eigenvalue and a similar thing, except on the right-hand side, there's no operator. So it's just the product of these two basis functions and the integral of those things. And again, because I can choose the basis functions, I can choose the test functions, I can definitely choose this to be something really simple that I know about. All right? So that's the transformation. And so if I call this matrix, the matrix Mn, that's the matrix of all these integral values, I'll call that A. This is like a matrix A times C is equal to this scalar, V of R, times another matrix, which is this matrix here, times C. And so that's a generalized eigenvalue problem. And if you use things like LinPack, LAPack, stuff like that, they have programs that solve those things pretty fast. And so to start with, it looks not so bad. You can do this. Now, the downside is that because this wave function is a function of 100 variables, you need quite a gigantic basis set expansion to accurately represent that wave function, unless you're really brilliant about choosing the basis functions. If you're really brilliant, right, you chose the basis function to be the exact wave function solution, you'd only need one term because it would match perfectly right away. But we're not that brilliant. So instead, we might need literally a billion terms. So 10 to the 9th basis functions is not unusual in this business. So now I have a matrix, a simple matrix equation, except the problem is it's a billion by billion matrix, 10 to the 9th by 10 to the 9th. Okay, so now you can see the problem. So I'm not just going to use LinPack and tell it to, here's my billion by billion matrix, and store that all in memory. That's 10 to the 18th elements in it. All right, so that's not the way it's going to go. All right, so instead, the people who work in this field have developed really sophisticated and complicated numerical methods specialized for exactly this particular form of matrix that you get for this problem that are only trying to get the lowest eigenvalue. And don't worry about the other ones. Don't worry about the eigenvectors. We don't need to know them. All we need to know is the eigenvalue. And use all special tricks that you can imagine to try to keep this under control. Because normally if you do an eigenvalue problem, how do you guys know how much CPU time it takes to do an eigenvalue problem? You have an n by n matrix. What's this? How much is the scaling? How much? N squared or n cubed, right? So depending on exactly how you do it. So, so if you have something like that, if it's 10 to the 9th, and you need something that's like 10 to the 9th cubed, that'd be 10 to the 27th operations. And again, you're already having trouble, right? Even 10 to the 18th operations is not so good. Anyway, so you don't want to just go and brute force solve for all the eigenvalues, and there's just all kinds of special tricks about how to do this. But the biggest trick is to try to keep this basis function really, really close to the reality. If it's very close to the real wave function, you won't need very many terms, and you'll have a pretty good solution. And in particular, people spend a lot of effort trying to get the very first term in this expansion, try to make that very first term look really like the wave function. Because if that's true, then the rest of the terms are kind of like perturbative, and that allows you a lot of like special tricks to solve the things faster. All right. So there's a field of people who all they do all day is try to solve this equation. Okay? And then they have conferences, they give out prizes, they have journals. There's a whole big community. That's all they do. And they try to think of new approximations and new basis functions that they can use and new numerical methods and try to implement them and show they actually work. And it's a big community because this is such an important problem because we have a lot of molecules in the world. Right? You're sitting on a chair, it's made of molecules. You know, I'm breathing the air, it's made of molecules. I'm made of molecules. I mean, molecules are everywhere. We would really like to be able to compute this V of R. It's going to help us a lot to predict a lot of things. So it's worth a lot of effort. And the good thing about this equation, it's basically the same equation for everything. Because all it is you add up the electrostatic terms of nuclei interacting with electrons, and you add the kinetic energy. And that PDE looks the same for basically every single problem in the world. Just the number of terms depends on how many atoms you have, how many electrons. But otherwise, it's just the same. So the form of this equation is always exactly the same. It has very special symmetry properties. It's actually a linear differential operator, so that gives you some special tricks. So there's a lot of good things about it, and very kind of specialized. After many years of work, so people have been working on this pretty hard since about 1935, when the first guy, I think he got the Nobel Prize for the first approximation that was semi-good for doing this. So it's been, how long has that been? 82 years? Something like 82 years. People have been working on trying to numerically solve this problem. I think Schrodinger wrote the equation in 28 or 29. So it's been not quite 100 years yet, but it's been a while. Many generations of graduate students have tried to do this problem. And what they found, for a long time, people thought that the best way was to write the basis functions as a product of functions of 3 variables, x, y, z. And so they said, well, I have a function of 100 electrons, so it's got 300 variables, but I'll write it as a product of 100 functions, each of 3 variables. And if you write it that way, it turns out it's relatively simple to satisfy all the physicality constraints and the symmetry conditions and everything. And so you can guarantee that your solution is going to be physical. It won't violate any of the constraints. And if you do it, you also can guarantee that whatever solution you get for V of R will be guaranteed to be an upper bound on the true value of V of R. So it gives you a way to tell if you're doing better. And in fact, if you add more basis functions, if you have some basis function, you add a few more, V of R will always drop because you get closer to the truth. And so you have like a systematic way that you can keep on making. If your computer gets better, bigger, your numerical method's faster, you can include more terms. You always make your V of R get closer and closer to the true value. So that's a really nice property. And so a lot of people worked in this way for a really long time. So I think this was like the main way up until about 1990 or so. So for like 60 years or something, this is the way people did it. And it's still a pretty good method. So that's the kind of the simplistic way. And you just be simple. You set that these basis functions just be the same as your test functions. Right? So you don't have to worry about one set of basis functions, and that's it. And this method is called configuration interaction, or CI. And then there's I don't know, a very large number of papers, at least thousands, maybe hundreds of thousands of papers, of people giving discussions about these basis functions and exactly which V's you should choose. That would be the best. and numerical tests about different choices of those. And the ones that were really good, people found certain basis functions were really excellent for doing this problem and gave good accuracy. They got special names, special acronyms. And you can write these short little acronyms, and everybody in the world knows that it means exactly this set of basis functions, which might be a very complicated function. But it's somebody wrote a paper, their initials got to be in the name or something. They figured out because everybody saw, wow, that's a great basis set for solving this problem. Okay, so that's sort of, that was like the mainstream for a long time. These basis functions turned out that people decided that the best way to do it is write these as polynomials in XYZ times Gaussians in XYZ. And they would center the Gaussians on the positions of the nuclei. So you've chosen your positions of the nuclei, capital R, and then you center a Gaussian on top of that nuclei, and that tends to make a function naturally peak at the position of the nuclei, which makes sense physically, right? The electrons want to spend a lot of time around the nuclei. So that sort of makes the shape naturally match the shape of the function to begin with. And then they do clever stuff about which polynomials to choose and which Gaussians to choose to make it drop off the right way. That's sort of like physically the way the electrons drop off as they go away from the nucleus. And the polynomials are a complete orthogonal set and cleverly chosen so that you can do a lot of the integrals analytically with a very small number of operations. So you can actually do this in a practically for pretty big systems. And so literally you can buy codes that will do it with a billion basis set expansion for these problems, and there's a lot of papers published with that kind of stuff. Then recently, maybe 10 years ago, people realized that the problem with this method is that this function is finite when two electrons are at exactly the same position. It's actually only when two electrons of opposite spin are at the same position. This thing is non-zero. Actually, the way people did it, they already knew that if two electrons of the same spin, they wouldn't allow them to be at the same position. That's actually required by the Pauli's principle. So that was already covered. But for two electrons of opposite spin, this wave function allows them to be exactly the same position. But it doesn't make much sense physically, because if the two electrons are right on top of each other, the repulsion between them would be infinite. And so the system would have an infinite energy, and that can't be right. So those infinities that were hidden in this basis representation turned out to give a lot of headaches, and basically meant that you couldn't really get very good accuracy, because you're doing a lot of effort to try to get the infinities to cancel each other out. And you have a lot of infinities in your integrands. So people discovered if instead you pre-multiply this kind of basis function times this factor, where this is for all the pairs of electrons, electron 1, electron 2, electron 1, electron 427, however many electrons you got. If you add in a whole bunch of factors like this, these factors are designed so that when these two r's are equal, the positions of the two electrons are the same, this thing goes to 0. So this is like a function that you multiply in that just puts zeros on top of all your infinities. And if you use the right unit system, this actually turns out to drop off the right way. So it's not just exactly at the point when they hit each other, but even close to that, what's called the cusp, when the two electrons are on top of each other. It gets rid of the cusp. And that turns out to really increase the fidelity of your basis functions to be similar to the real physical solutions. And so you can get away with many fewer terms in your basis set expansion because your basis functions are already much closer to the real solution. And these methods are called F12 methods. If you ever see F12, that's what it is. So that's like been the big advance, I think, in the last decade, is people have written efficient numerical codes that include this. Now this thing is not the easiest thing to integrate. And so they had to spend a lot of effort to figure out how they're going to compute these integrals like this when the basis functions include that horrible product of a bazillion pairwise terms, as well as all these other terms over here, right? So it's a really complicated basis function. But hard-working graduate students somewhere, actually more than one university, wrote out all the integrals, figured out good ways, good schemes to evaluate all those integrals. And so they have numerical methods that actually evaluate all these really complicated multidimensional integrals. And so then you can construct the basis. Then the next thing, the other thing that happened, this actually happened, it was first discovered in the 1960s, but it took a long time for people to accept that this was a better way to go. So people were really stuck on doing this CI method. This idea that you have this variational bound in the energy is very attractive because it really gives you a quick way to tell if am I making any progress towards solving the problem. If the energy goes down, I'm doing well. But it turns out that this other approach, called the coupler cluster approach, it actually turns out to work better in practice. And so I'll try to explain. So the idea is instead of explicitly constructing the linear combinations of the basis functions as you would do in the CI method, so in the CI method, we write down this matrix equation. And then if you know how eigenvalue programs work, is they kind of rotate the basis. They take linear combinations of, they multiply like the matrix on both sides by something, a similarity transform, and it really changes your basis set. And then you get it, and you keep doing that iteratively over and over. That's how the eigenvalue programs work. Instead of doing it that way, they say, let's write the operator inside our integrals. And so would they change everywhere you saw h before, let's do a similarity transformed h. And then they very cleverly chose exactly what t operator you want here to make this kind of physically and match up with what they had learned from doing the CI methods about what the solution should look like. So they cleverly chose a t, and then they said, let's do it like a similarity transform of the actual operator rather than of the matrix afterwards during the solution procedure. And so now I have this thing h prime, which is this transformed h. And it now depends on some coefficients that I'm going to vary. So instead of varying coefficients in my basis expansion, I'm going to vary coefficients in my transformation of my matrix. And so I'm trying to transform the matrix to sort of line it up. Instead of rotating the basis functions to line it up with the operator, I'm trying to rotate my operator to line it up with the basis function. So if that makes any sense. So I choose my basis function that's my best guess of my wave function to begin with, and then I kind of rotate my operator to try to line it up with that, so that the operator lines up to make, you have an eigenvalue, eigenvector, and they have to line up, this kind of thing. All right. And then I still have test functions on the left. The test function will have some more story about that. And now, because I'm doing it this way, this is no longer a linear algebra problem, because these c's are actually inside the exponents of these exponentials. And these are like operators. This is quite a complicated thing. And because of that, the whole thing is like nonlinear in C. You can see there's two c's to begin with, right? One on each side. And so it turns out that this kind of form, which looks a lot like what I had before, but now it's different because of the c inside here. This is now a nonlinear system of algebraic equations. And it's still really large. So in principle, it's like as large as it was for the CI problem. So it might still be 1 billion terms or something. So there's 1 billion C's. And so this is a pretty hard system of nonlinear algebraic equations, because you have a 10 to the 9th simultaneous equations and 10 to the 9th variables to solve. But you could do it. And this method does not give an upper bound on V. So I don't really know if I'm improving my solution if I change something, because the computed value of V will go up and down. And usually I don't know what the true solution is. So this is a very disadvantageous part of this procedure from the point of view of trying to know if you're making any advance. You have to actually sort of know experimentally what the solution is, or somebody else has to compute some other way and tell you what the true energy is to know whether you're getting close to the real V of R. But it does guarantee this other property called size extensivity, which means that if you if you replicate a system, you have like a pair of molecules instead of a single molecule, you'd expect the energy value should be twice the potential energy of this guy plus the potential energy of this guy. But it turns out that the previous variational method doesn't do that. It gives you an energy that's actually like a little bit lower than double. of the before, which has totally confused people for a long time. But this one is guaranteed to satisfy that property. Empirically, people have found that if you use the same number of unknown coefficients, you get a better number. And if you also use the F12 basis, you get a really good number that's very close to experiment of what the energies are of interactions. So I'd say that this method, there's some theoretical argument about why it should be good, but the real argument is people have tried it and it works really well. So this is the method that in my group currently we think is our best method, or our main kind of good method. This couple cluster thing, you have a lot of choices still about exactly how big the basis set is and exactly how you do this transformation thing, what your T is. And each of those has a different acronym of all the different approximations people have tried. And there's one of them that's called CCSD, which is very popular and has been implemented a lot. And then this parentheses T things means that they take some extra terms and treat them perturbatively, sort of the next leading term. And that combination turns out to be really good, particularly if you use it with this F12 basis thing. And this gives you very good accuracy, but it's expensive. So the CPU time required scales is about the 7th power of the number of electrons in your molecule. So if you double the number of electrons, the CPU time will go up by a factor of 2 to the 7th power. Sorry, what? So this is like the DNS codes that run on the supercomputers, and the biggest supercomputers in the world. So this is for the similar scale of computation. You need basically the biggest computers in the world are running very many cycles for these programs right now. And this is one of the biggest consumers of computing power in the world, even probably more than video games. So. Yeah, because this is Now you can run it. You have a lot of choices about exactly how big your basis set is, and if you use smaller basis sets, you can run it even on your PC. But if you want good accuracy, it's a very significant calculation to do it. And the only reason why you would use this method is you want good accuracy, because it's like this is a heck of a lot of work. So if you can do all this work, you might as well get a good number at the end. All right. So I hope you got the message at the headline here. That quantum chemistry is really complicated. And I haven't even tried to explain about electron spin and the Pauli conditions. That's just like another whole lecture in itself about trying to explain what that is exactly and how you handle it. But fortunately, the quantum chemists have been working hard for a long time. And they figured out pretty good methods to solve this, to compute VFR. And most importantly, they provided a lot of really good codes. User production quality codes. Some of them even have a helpline you can call up if you have problems with the software. And not too expensive, the programs. And they've tested them out. And so you actually can get a pretty good idea of their accuracy for a lot of kinds of common problems. Because they've carefully compared them to experiment. They compared them to higher level calculations. And so there's a whole literature about trying to judge how accurate the different approximate methods are. Also, how much time they take, how much memory they take. They spend a lot of time on all this kind of stuff. However, this is still software primarily written by graduate students. So it is not perfect. But I would say, in general, it's better than what you can get for CFD software. So, and in particular, a very important thing is if you take two programs and you tell them the exact same acronym for the same basis set and the exact same acronym for the same approximations to use when solving it, and you press go with the two programs, they'll take different amount of time and different amount of memory to solve it. But the number you get will usually agree to like 5 or 6 significant figures. So I would say that's better than my experience with CFD codes, where if I buy a CFD code from Fluent and a CFD code from somebody else, in fact, if I buy them both from ANSYS, from two different divisions of ANSYS, and I run them against each other, you'll be lucky if you get the same numerical solution, each to more than 1 or 2 significant figures. but the quantum codes have been pretty carefully tested. So most of the time, they'll agree. And so you almost don't have to tell, you almost don't have to tell what code you use to compute it. You can say just the name of the acronym and what approximation you used and what basis set you used. And that's enough for somebody else to replicate what you did. However, not always. And I had a very sad experience where I used a certain program not to be named. And I got some results, and I published them, and the reviewers thought they were great. And I published it, and then later, other people tried to replicate my results, and they could never replicate it. And then 3 other groups published papers. Green is full of baloney. He says his numbers are crazy. Here's the real numbers. And we tracked it down, and it was a version release of the same program. And so there apparently had been a bug, and they fixed it, and they changed the version. But they didn't even update the version number. They still called it the same version number, but it was a different code. You could do a diff the 2 of them. They're different. So they had fixed a bug, and in my release, I was using the buggy version, and they fixed it later. So it's that kind of stuff is still going on in that field. Also, if you, for example, using the coupled cluster method, you're solving a system of nonlinear algebraic equations, a very large and difficult system of nonlinear algebraic equations. It is definitely possible that there are multiple solutions. And it's also possible by Murphy's law that when you try it, you'll converge to the non-physical solution. And then your competitor, when they try it, they'll converge to the physical solution. And then they'll publish and say, why are you full of baloney? So just be aware that this is it's not, these programs are not like the 10 Commandments that God wrote in the stones, and brought down from the mountain. These are like graduate students wrote it, just like you. And some people checked it a few times, and it's pretty good, and they sell it for money. But it's not like certified, guaranteed, always correct software. But usually, you'll get V of R values which agree between all the programs to many significant figures. And so typically, the error is mostly due to the actual approximation basis set, which you chose. You tell it, use this approximation, use this basis set. And so it's your fault, right? If you get a number that's not accurate enough, you told it what to do, and it just did it. And usually, the programs correctly compute that number, right? And usually, it's nothing to do with the implementation inside it. It's completely about you. Just like if you do a CFD, if you did it correctly, a DNS, you'd expect it mostly has to do with what your mesh size was, right? And maybe something about how you specified your boundary conditions or something. That should be it, right? You should get the solution. There's a certain solution of the PDE. And so if you get a bad number, maybe it's because you didn't try to make the mesh fine enough. It's a similar thing here. If you make your basis set too small, you'll get a bad number. And it's up to you to decide what basis set you want to use. There's many of these packages that you can get. And some of the famous ones are called Gaussian and MulPro. And I think Gaussian in particular has a really big market share. And so you'll see lots and lots of papers say they use Gaussian. Again, the Gaussian is a program that can run many, many different approximations and many, many different basis sets. And so just saying that somebody says, I did the calculation with Gaussian does not tell you if it's accurate or not. You have to say, well, which calculation did you do with Gaussian? Which approximation did you ask it to do? Did you do coupled cluster or CI? Did you do F12 or not? What basis set size did you use? It's not sufficient just to say I use this software, because it's just like you said, I used OpenFOAM. It doesn't tell you how good your solution is going to be of your CFD program, right? All right. Yeah, and there's many other ones too. And some of them are free. If you have no money, there's our free quantum chemistry packages as well. And some of them parallelize well, and some don't. There's a whole complicated story. And if you're interested, I or some other people in the audience can tell you about different packages, and they have pluses and minuses for particular types of problems. But basically, they're available. All right, so let's suppose that you got yourself a quantum chemistry package, and you learned how, and you can compute V of R as accurately as you need. And you still haven't computed the energy levels, right? The whole purpose of this whole discussion here, back at the beginning, was how we compute the energy levels. So I went off on digression and told you all about how to compute V of R. So let's suppose you can do it. So how do you do it? So the way it's usually done is people make what's called the rigid rotor harmonic oscillator approximation, RRHO, rigid rotor harmonic oscillator. So first thing they do is you assume ideal gas, which means you assume your molecule is just floating around in space, and it just bumps into the walls. And it doesn't hit any of the other molecules, and it doesn't feel the other molecules. Perfect ideal gas. So then you can say that you can separate out the overall center of mass translation of your molecule as a degree of freedom that's totally separate from everything else. And then you can actually solve the nuclear motion Schrodinger equation for a particle moving freely. And it turns out that its energy levels follow this pattern, that the ends are the integers, and any sum of the square of the three integers adds up, gives you a loud quantum value. And then the energy scaling is the Planck's constant squared divided 8 times the mass of the molecule times the, I think it should be L cubed. Maybe it's L squared. I don't know. We should double check in the textbook, make sure I didn't have a typo here. Okay. I guess else, I'm not sure. Double check in the textbook. All right. So you put that formula in, and you plug that energy value into the expression for the partition function, and you can get a thing called the translational partition function. It's just a partition function due to the translational degrees of freedom. And it turns out that sum is a little bit inconvenient, but the integral version of it has analytical solution. And because the translational energy levels are so closely spaced compared to KT, it's valid to replace the sum by an integral and treat it as a continuous variable. And so you can get this expression at the bottom for the translational partition function. All right, so that's first part. Then the second part is rotation. So we think the molecule can rotate in space freely. We approximate it as a rigid rotator, which means that the atoms, if it's spinning, the centrifugal force is negligible. And the Coriolis force, due to the fact that it might be vibrating and rotating at the same time, is negligible. We just leave those out. And all we have is the fact that it's just rotating. And that's really what we're just doing, is assuming that the bonds are so stiff that you don't significantly change the moments of inertia through the course of a vibration or anything. The moments of inertia are basically locked because the molecules just vibrate tightly around their equilibrium geometry. It's sort of assuming that the valley in V of R is very steep. So the molecule spends all its time down the very bottom of the valley and doesn't really get up very far. And so if all the vibrations are small amplitude, nothing is floppy in the molecule, it's all kind of rigid, then you can assume that the moments of inertia just have a certain number. And if we have a rigid rotator with a certain moment of inertia, you can go ahead and just solve for the energy levels of that in quantum mechanics. And this is the expression. It's pretty easy. And it gives you expression for the G's too. And then you can do the same approximations we made for translation and get a very similar expression for the free rotation of the molecule. And if you have a nonlinear molecule, there'll be 3 distinct moments of inertia, the 3 principal axes, A, B, and C we call them. And you just take the same formula, you replace the I by the square root of the product of the 3 moments of inertia, and you get an extra factor of square root of pi if you do all the math carefully. All right, and that's it. So you have expression for a regular molecule, nonlinear. If you have a linear one, it's a slightly different expression. There's a symmetry number, should be one here too, that's has to do with if the molecule is symmetrical like H2, when it rotates halfway around, it looks just the same as it started. And because of that, the states are what are called indistinguishable. And in quantum mechanics, they're not different states. Those two are exactly the same thing. And because of that, you'd have to divide the Q that you would compute with classical mechanics by a factor of 2 to make up for the symmetry. And so that's what these symmetry numbers do. Exactly getting the symmetry numbers right is another whole lecture by itself. I won't tell you about that now. But there are some programs that can suggest what they think the symmetry numbers are. And then if you want to, you can take a graduate course about symmetry and try to figure out what they really are. But they're just integers, so usually the factors of 2 and 3. All right. So we dealt with the translation, we dealt with the rotation. Now most of the motions in a molecule are typically the vibrations. So there's 3 times the number of atoms minus 6 motions that are vibrations, functions of the internal coordinates. And these things are the things that really depend on V of R. And so we need to know V of R. Now if we assume that they're all small amplitude, tiny little vibrations, then it's reasonable to just do a Taylor expansion of V of R about the equilibrium geometry. So if we assume the value is very steep, we assume the amplitudes of vibrations are very small, then we can say that basically that the positions of the atoms will be at the equilibrium geometry plus a little deltas. And we can just do the low order Taylor expansions in the deltas. And it turns out that the first order term is a quadratic term in the deltas of the displacements. And because it's a quadratic expression, this turns out to be the same as a normal mode problem in classical physics. How many of you guys have done normal modes in classical physics? Anybody? They teach this in mechanical engineering anywhere? Natural vibrations? No, never heard of such a thing? If you have a violin, it has like certain frequencies it wants to vibrate at? Yeah, you've heard of this, okay. All right, well anyway, it's a classic physics thing, very straightforward to calculate what the vibrational frequencies are. You build a bridge, you have to know what the natural frequencies are, because otherwise if people march across and they march at the right time in the bridge, you make the bridge fall down. Anyway, so that's a very old problem. It's been solved, and it provides a natural choice of coordinate transformation. There's like natural coordinates that correspond to the natural vibrational frequencies of the molecule. And those choice get rid of the cross terms in the quadratics. So you have a second order expansion of V. There's cross terms between motion 1 and motion 2. But if you cleverly choose your coordinate system, you can actually make all those cross terms disappear. And so now the thing becomes a decoupled, a separable differential equation system. And it has a very simple solution. And the solution is that the energies are an integer plus a half times Planck's constant times the natural vibrational frequency as computed by classical normal mode analysis. And this is all coming from the fact that we're just doing the second order Taylor expansion. The real V of R is definitely not a perfect quadratic. It's some really complicated function. But we're just doing the little Taylor expansion around the equilibrium geometry, and you can definitely do that. And if you believe, to the extent you believe that true, then this is the real expression for the energies. You have to worry now about zero of energy. So notice that when n is equal to 0, which is the lowest state, this vibrational energy is not equal to 0. So it's very different than classical physics. In classical physics, I have a violin. It can just be stationary. It doesn't have to be vibrating, right? The violin can just sit there, and there is a state where it's just sitting there, it's not making any noise at all. It's just peacefully sitting there. This state does not exist in quantum mechanics. In quantum mechanics, every vibration is actually always vibrating a little bit. And it's just very little bit, because it's related to Planck's constant, which is like a really small number. But it's actually molecules that actually is pretty significant. And so then you have to decide what your zero of energy is going to be. Is it going to be the classical one where the vibrations have no energy? Or is it going to be the quantum mechanical one where they have what's called the 0 point energy, where all of the ends are chosen to be 0 for all the vibrations, but you'll still have all the sum of these half times h nu of all the frequencies in your molecule? And I suggest that you should use the 0 point energy. So choose a 0 to be the lowest physical state, where all the ends are 0. You'll have the sum of a half. And if you do that, then you can rewrite this equation this way, that EVIB is just equal to h times n. You get rid of all these halves, because I've sort of pulled those halves out of the problem. And this is the energy of vibration above the 0 point energy. And then the partition function for the vibrational modes takes this particularly simple form here. And it also has the nice property that as t goes to, which way? T goes to 0, this exponent goes to infinity. This means this whole term goes to 0. It means q goes to 1. So with that choice of the 0 of energy, as t goes to 0, all the molecules will be in that state, the lowest energy state. And then you'd expect the partition function to be 1. At least that's what I would expect, because there's only one state. And so this choice of zero of energy makes that sense. If you choose a difference of zero of energy, you get some really crazy t dependence as t goes to 0. All right. So now we have an expression for the vibrational partition function. We also have one for the rotational partition function. We have one for the translational partition function. Oh, but I forgot. We have to tell you, where the heck did we get these V's? So we can sometimes get them from experiment. So that's what IR spectroscopy is about. IR spectroscopy is measuring the vibrations of molecules. And if you're fortunate, your molecule will have all of its vibrations will have a strong enough intensity in the IR spectrum that you can measure them all. And you'll get all the vibrational frequencies that way. So that's the real experimental one. But most often, this is not possible. Usually molecules are so big that if you do the IR spectrum, it turns out that some of the modes have like no absorption strength. So you look in the IR spectrum, you just don't see the vibration. Also, the spectra look really complicated. There's lots of vibrations. And sometimes two of the vibrations are right on top of each other, and you can't tell them apart. So you don't know, you have a missing, the number of peaks is less than the total number of vibrations you expect, and you don't know which one is the missing one. So experimentally, it's quite hard to do this. So instead, more commonly, you have to calculate them. Now, in the old days, what people did was, from experience from IR spectroscopy, they know that a CC bond stretch always has a frequency about such and such. A methyl group always has 3 vibrational frequencies that look such and such. And they had like rules of thumb about different functional groups, what vibrational frequencies they usually have. And they're pretty good rules of thumb. And so you can get a pretty good idea of the frequencies. But it turns out that sometimes there's a few frequencies that are kind of oddball, and you can't predict them very well. Another thing is you can just look. People have studied this for a long time. They care about V of R since 1930s. And they have approximate formulas for it. And the people who are doing vibrational spectroscopy worry about this a lot. And you've probably heard of these force fields, UFF and MM something or other, and charm. There's all these different force fields that people can use. And so that's another way to try to compute the frequencies. And that works pretty well for stable closed shell organic molecules, because people study that class of molecules a lot. But if you have some strange element in your molecule, then nobody will know what the frequencies are supposed to be. If you have a free radical or an ion or some wacko molecule, then again, no one will have any idea, because all this stuff is based on empiricism. They previously studied a lot of other molecules, and from that, they rigged up a force field. For small molecules, you can go ahead and use things like CCSD, like I just talked to you about, and you get great accuracy. So you can get really great vibrational frequencies by doing that. But the calculation scales as the number of electrons to the 7th power, even a little bit worse than that, actually, because I need to do a lot of calculations to get all the displacements to get my Taylor expansion. And so unless you have a good CPU budget, this might not be your first choice. So the most common approach is they use a different kind of calculation called a DFT calculation. How many people in this room have done a DFT calculation? Oh, man, we got to get you guys on the stick. OK. We'll get some more people to do that. So there's some acronyms you might have seen before, things like B3LIP. I think it's maybe the most popular one. Another one, MO62X. This is another quantum chemist case where somebody makes up an approximation, and they get to write down the acronym that's going to be for that approximation. Everybody then just uses that acronym instead of trying to explain the approximation, which might be 10 pages in a journal paper to explain what the approximation is. So anyway, these approximations turned out to be very successful. They're pretty accurate, not very expensive, and also they're implemented in codes that a lot of people have access to. And so they get widely used. So there's the thousands and thousands of papers that have used this approximation, for example. So you can buy a computer program that computes frequencies using this method that maybe it costs you $100, and the numbers are great. They're really good. So if you then predict the spectrum and you go to your friend, the IR spectrometer, guy with an IR spectrometer, and say, please measure my molecule, and you tell them your frequencies, you'll be pretty close to all the positions of all the spectra that they'll see. So this is a really very successful thing. And also, the calculations, the programs are great. They're set up to do the whole thing automatically. You don't have to know anything, and it doesn't take much time, so you can do this on your PC. So this has been like a huge breakthrough in this field since the 1990s, that you can now, anybody can just buy on their PC, press go, in less than an hour, they'll have the vibrational spectrum, probably faster than you could actually get the molecules, put them in your FTIR and measure it. You can get it, and this way you'll get all the frequencies. With the FTIR, you'll probably have trouble assigning them and figuring out your spectrum. Okay, so what the heck is DFT? So Schrodinger wrote down this equation that gives, if you knew the wave function, it tells you how to compute the energy. And the methods like the CI method, we're varying the wave function and trying to minimize the energy, right? That's why I told you how the CI method guarantees to give you an upper bound, and you keep trying different basis expansions to try to get a better estimate of the wave function, and each time you do it better and better, you get a lower energy. So that's what Schrodinger told us how to do. But this wave function is a function of 3 times the number of electrons variables, which is the positions of all the electrons. So for something like benzene, it turns out you have 126 variables because you have so many electrons. So this is pretty hard. It's hard to find the very best possible function of 126 variables. This is a very complicated function. And so this has been the problem. Now back in the 60s, Hohenberg and Kohn proved that you don't have to do it with a wave function. You can actually do it with just the electron density. The electron density is only a function of 3 coordinates, x, y, z. So this is a much more practical thing. If you have E of rho, it's a lot easier to vary a function of 3 variables than it is to vary a function of 126 variables. So this is like trivial by comparison. However, unfortunately, all they gave was the existence proof. They proved that there is a functional E of rho, and in fact, it's the same for all molecules. They proved there's a certain functional, works for every system. But they didn't tell you what it was. They just proved it existed. This is like typical mathematician stuff, right? They always do this. So there is a functional, this is called the density functional. But then Kohn went on, and with sham, he suggested a good way to try to construct E of rhos that are pretty good. And instead of working with rho directly, he said, let's work with these orbitals, other functions of 3 variables, but let's have 1 for each electron, and write rho as a sum of the squares of these guys. And if you do it that way, it turns out that the most difficult term in the E of rho expression, you now get a really good way to approximate it. And so this turns out to be the way that everybody does it now. And this is still easier, right? So now I have a number of electron basis functions, orbitals, n is from 1 to the number of electrons. So I have, instead of 126, a function of 126 variables, I have like 42 functions, each of 3 variables. Now, that might not sound like I really got anywhere, but actually that's a lot simpler. That 42 different functions of 3 variables is much, 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 much easier to handle than 1 function of 126 coupled variables. Because it's sort of like you've separated into 42 sets. You've separated all these variables into 42 little subsets, and each one's a small little subset, and you can deal with it. So this is still pretty good. Now, Kohn and Sham figured out how to deal with the biggest term in E of rho that was hard to deal with. But there were still some terms left that nobody knew how to estimate what they were. So they knew such an E of rho existed, but they didn't know what they were. But then in the 1980s, some people cleverly guessed what the form of E of rho should look like. That'd be a pretty good approximation. And they discovered these things. And then in like the late 80s, this one was invented, and this one also. And then in the last decade, this one was invented. And people keep on inventing better and better approximate E of rhos. So they know that it exists. There is a true one that exists, but we don't know what it is. But they try to find the best approximate functional that gets closer and closer to the true one. And that's like again, there's like a whole subfield of functionalists, people who try to think of functionals. And you can read a lot of papers about this and how you can try to figure out, how you can guess how to do this. But anyway, Even I, in my spare time once, I wrote a functional. It's a fun activity. But you know it exists, you just don't know what it is. But anyway, if you get a good one, then it turns out to be a convenient and fairly accurate way to calculate V of R for not much CPU time. And that's the most important thing. It's really, you get a pretty good accuracy and really very little CPU time. So that's really fantastic for approximations. All right, so all these programs that I mentioned before also do DFT. And in particular, they compute the energy, and they also compute the derivatives of the energy with respect to all the nuclear motions. And that second thing, the derivatives, are exactly what you need first to find the equilibrium geometry, because you want to minimize V of R to find the positions of the atoms that minimizes the potential energy. That's your valley bottom. And then you want to be able to do the Taylor expansion around that valley bottom to get the frequencies. And these programs know that that's what you want to do. So they have it all set up automatically. You press go, boom, and then you come back an hour later, and it tells you the geometry, and it tells you the vibrational frequencies, all computed, because it went through all that math. And actually, they'll even tell you all the thermal properties, because they know that's what you want. So they'll tell you the entropy, they'll tell you heat capacity, they'll tell you everything you want to know. The way they do the minima, let's see. So with the gradient, you can go downhill to find the minimum energy geometry we call arc equilibrium. And usually this is found using an optimization method called BFGS. If you don't know what BFGS is, you should look it up. It's really clever. So it's a really nice minimization program. But you have to give it an initial guess geometry. So this is where you have to do some work. The quantum chemists have written this nice program, but as input, you have to give it a guess geometry. If your guess geometry is too far from the true geometry of the molecule, the poor optimizer is going to get lost, and you'll get baloney stuff out. So you have to have a pretty good idea of what the molecule looks like. And beware, there are almost always multiple local minima on V of R. So if you give it a guess and it converges, and it gives you a molecular geometry, it does not mean that that's the geometry that you wanted for your molecule. It just means that that's one of the geometries that's a local minima on V of R. And so you might have to hunt around and try different initial guesses to find the one that finds the global minimum. And it's a nonlinear system. So in general, you have no way to prove that you've actually found the global minimum. So you just try until you get tired of trying. And then you publish it and say, and I hope somebody doesn't discover a lower one and publish and say, Green's fouled up again, publishes unphysical minima geometry. Okay? All right. So the key is you have to be close enough. You have to really be in the valley that corresponds to your molecule you care about. Be aware that your valley is often connected to some other local minima by pretty low ridges. And if the ridges are low enough, we call those things conformers. And we mentioned that yesterday, right? That for like acid aldehyde, the methyl group can kind of rotate around, and there's different orientations of the methyl group relative to the HCO group. And all of them have pretty low energies. And at normal temperatures, actually that methyl group is like spinning around. It can access them all. But if you look at V of R, it goes up and down, has like a little corrugated bottom as the thing's spinning around. And that's just in that simple little molecule. If you get a big molecule, you may have hundreds of local minima that are connected by such low barriers to each other that they're all accessible. And really, we would call them all one species at a combustion temperature, because at combustion temperature they would just interconvert, in a femtosecond time scale or picosecond time scale. All right. So sometimes you may sadly have to get into this problem, where you have to try to enumerate all the conformers and worry about this. Maybe later this week we'll deal with that headache. So to begin with, let's assume we have a small molecule. It doesn't have very many conformers. There's no trouble. We know what we're doing. You definitely want to know the lowest energy conformer, because that's really the equilibrium geometry. That's the one that's going to have the highest Boltzmann weighting. And it's helpful to find as many of the other ones as you can, because it turns out if you know them, you know what they are, you can actually make more and more accurate estimates of your thermochemistry. All right, so this is the Taylor expansion. The DFT program will calculate, it finds the equilibrium, then it computes its energy, then it computes the second derivatives. V with respect to each of the nuclear displacements, of the displacements of the atoms. This thing is called the force constant matrix. Sometimes people call it F. And a lot of quantum chemistry programs actually compute this thing analytically to make it faster. So they instead of doing finite differences, they actually analytically compute the second derivative. And if you remember, for a simple harmonic oscillator, the frequency is the square root of k over m. Do you guys remember this from high school physics? Yeah? OK, so this is the generalization of that in multiple dimensions. So I have a lot of atoms moving, a lot of degrees of freedom, but they're all harmonic oscillators. And it turns out that this mass-weighted, the F is kind of like the force constant k, and these m's are the right way to do this. This thing turns out to give you the square of the normal mode frequency, because this is sort of like k over m. So you just find the eigenvalues of this matrix, and that tells you all the vibrational frequencies that you need. And the whole thing is done automatically for you in Gaussian and many, many other quantum chemistry packages. And basically all you need is guess at the equilibrium geometry, tell what functional to go, what basis set to use, press go get a cup of coffee, and you come back and it tells you all the thermal properties of your molecule. So that's pretty nice. All right. And I should say that the weakness of this whole thing is one thing is this conformer problem. That's one weakness. Another one is that we're assuming only small amplitude motions. If you actually have a molecule that's floppy, then these approximations aren't going to be right, and we have to do something else. And also, this gives you, in principle, all the thermo, but the enthalpy number is suspect and not referenced to anything sensible, typically. So a lot of times, if you just use a DFT method, the enthalpy number is not good enough. The entropy, the heat capacity, they'll be fine, typically. And so this is great for entropy and heat capacity. But if you want to do, we'll get into what you have to do. You have to do basically a better method, because DFT is not really accurate enough. So DFT gets very good numbers for the geometry and for the second derivatives of V around the geometry, but it's not so good for figuring out things that totally break bonds. And so which is what you get into if you're trying to reference your species to the elements in the standard state. You have to consider about breaking bonds, and the DFT method is not very accurate for giving those energetics. So you have to do a different method like CCSDT, 1F, F12, things like that I talked about before. All right. OK, so here we go. Yeah, beware. A lot of people publish papers using RRHO. OK, so one reason is any stupid graduate student can buy a copy of Gaussian for $75. Sometimes they give it to you free at your university. And they can put it on their laptop, and they press go. Boom, it prints out. The entropy is equal to whatever. That's at the bottom of this huge output deck. So the student's lazy. First of all, they don't even look at the rest of the output deck. They just go right to the bottom. Boom. All I wanted to know was the entropy. That's why I wanted to publish in my paper. And you read it off. Heat capacity. OK. And they don't read, first of all, on line 20 of the output deck, it said, warning, such and such didn't converge. Warning, numerical problem in step 37. Right, so that's one common failing. But even then, if suppose there's no warning, everything converges, it's all nice, it's Bing, the assumption that was made inside Gaussian was this rigid rotor harmonic oscillator, which assumes that there's no large amplitude motions, and actually doesn't even pay attention to conformers. It doesn't even know about it. And so a lot of people will just go ahead and type that, whatever prints out in that box, they will just transcribe it into the journal article, or transcribe it into their ChemKin input deck. And then it'll get published as supplementary information in their combustion and flame paper. And then some poor graduate student somewhere else will download that kinetic model and use it for their predicting their system. And again, by Murphy's law, 100% of the time, the new graduate student who downloads this thing, who has no responsibility for the crappy number, is using it. It'll turn out that the most sensitive number in his system for his observable is that entropy value, which is completely wrong. OK? So just beware. Just because somebody writes a number with a lot of decimal places and puts it in a table, it does not mean that it is true. OK? I can type, tung, 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 tung. OK, I typed. I put it in the table. It doesn't mean it's true. Okay, truth is a lot more difficult than that. Anyway, a very common problem right now is that these RRHO numbers are too easy to calculate, and most of the time they're right, but not always. And so you have to be aware, and you basically have to look at your molecule and say, is there any way this molecule can distort that's not going to go uphill in energy? And if that's true, that means there's going to be a floppy motion that corresponds to that distortion. And then you have to do something else. And the most common one is torsions, internal rotations, like the methyl group rotations is a very common example. All right. So far, I've been talking about single molecules. You may have to stop. We'll take a break. Let's go take a break and get coffee.